All righty, looks like it's time to begin. Hello, welcome to our VEST Spring 2025 webinar series. I'm Megan O'Neill. I'm your moderator for today's webinar session. And today we will demonstrate and discuss some best practices for designing non-rectangular blocks using MDTools. This webinar will last approximately 45 minutes. You will be able to submit questions or comments at any time during the webinar by posting in the questions section located within your webinar control panel. Questions may be answered as they're posted, or we'll try to address them in the last 5 minutes of the webinar. Note that today's session is being recorded and that the audio is muted for all attendees. If you are experiencing any technical issues, please use the chat window and alert our support staff. Now it is my pleasure to introduce our speaker for today's webinar session, Carlo Molon. Carlo has worked in the hydraulics industry for many years and currently manages application sales and training for VEST desktop and cloud products. Carlo?
Thank you, Megan, for the introduction, and thank you all attendees for joining today's webinar. Today I'm going to use MDTools for SolidWorks. So for those having an Inventor, that's okay. Whichever commands I'm showing today is also available in MDTools for Inventor. But last time we did a non-rectangular manifold webinar, it was using Inventor version. So today I'm focusing on SolidWorks version. When we speak about non-rectangular block, we think at manifolds with different shapes than the standard rectangular one. The most simple, so I'm starting later, I'll jump to the exercise for today, but let me show you a bit of shapes, possible shapes. So when it's simply up to cutouts, chamfer, MDTools provides some commands to create strange shapes. As an example, I'm starting with my block, maybe a 200 millimeter by 150 by 150, and I need maybe a couple of cutouts. So there are commands in the MDTools ribbon for cutouts. As an example, I want a cutout on this face for a length of maybe 50 millimeter and a width of 30. We can see a preview, and I want a cutout through all. And then maybe I need also another cutout on this face. I can change reference. So as an example, I can change the X and Y. And again, I want maybe another 60 millimeter by 50 and through all. And maybe I need a chamfer down here, maybe at 30 millimeter. So whenever I have a shape like this, so I started from an MDTools block, then I created a shape, then here I can place cavity almost anywhere. So let's say that I need an FC8-2 HDAC component, a check valve, and I want to place it on the chamfer directly. It will be possible. So here the interface is slightly different between Inventor and SolidWorks. So it's a bit smarter in SolidWorks. So basically, when we click Move in SolidWorks, MDTools is able to find the origin, so it will be easier to move. In Inventor, for those that having familiarity with Inventor, they will need to pick X and Y position. But that's a minor difference. Basically, here we can move cavities, we can stretch drills, and we can place drills in any non-rectangular face. So as an example, I can change face and position the same drill on a different face, or I could copy and position on another face. And similarly, the commands for external port, for construction ports will work seamlessly. But this is quite a simple scenario. So whenever you require blocks with this kind of shapes, then you should be able to handle quite extensively with what we will learn today with the other aspect. So today I want to do something more difficult. So I'm going to do a cylindrical manifold. So basically, I'll use all these techniques to design a block that will fit into a cylinder. Actually, it will not be a cylinder itself. So while thinking at this exercise, I can see a question: how to change metric units to inch while starting with a block. So it's not possible to change the unit on a already designed block. So when you start placing it, it will be grayed out. If you start a new part, it will be possible to change the unit, design unit. So I stay with millimeter in any case. Of course, when we speak about designing manifolds, the unit is simply what the designer has more familiarity with, but the end result will be the same. Either you design a FC8-2 cavity in millimeters or in inches, that should be the same shape. So there will be no difference in the way we handle the design. But if you are familiar with inches, just feel free to change to inches. Let's get back to our exercise for today. So basically, I will not do a very complex manifold, although it will have some complexities on its own due to the shape of the block. Basically, I want to do a manifold that is assembling. So let me open the part of the cylinder. So I took from internet a cylinder, a standard cylinder. I found it in trace parts. I removed the cover end, and I created this pattern of M12 bolt holes, similar to these ones. So what I'm going to do today is I'm going to design a cover for this cylinder with all these mounting holes, and inside I will try to put some valves. So basically the valves will be a NG16 directional control valve and a counterbalance valve and some ports. So basically I want to embed this function directly into the cylinder. So my end result, if I open a whiteboard just to try to sketch what I'm going to use, I see another question, I'll jump to it shortly. So I'll have my cylinder here, and I will try to design my manifold here with the through bolt holes. And inside here, I will put my directional control valve, which I will put on the back end. So here I have the directional control valve, and I will enter somewhere on the top face with A, B, P, and T. And here we have the rod for the cylinder. So I'll start my design with something new that we have in latest library manager, because this is not really a standard footprint. This is something that I have made for the purpose of this exercise, and I'm going to show you a new functionality that is coming with the MDTools Library Manager 25. So basically, I have made this same interface in an MBXML file. Actually, in this case, I made with MDTools for Inventor, and I have exported my. I can export. I have exported my MBXML into a file. So let me go to the webinar, and that is my cylinder footprint. So for those already familiar with MDTools, within MDTools we have an exchange file format called MBXML, which allows us to exchange information between MDTools for Inventor and SolidWorks. And this MBXML file is an XML file that has all the information for the geometry. So in the new library manager, which I'm opening now, it is possible to import cavities not only from other libraries but also from MBXML file. So basically now, since that cavity is not present into my library yet, but was there in a design I already made, or I got from a colleague, or maybe I got it directly from Vest. They could send me an MBXML file. Now we have this possibility to import from the XML file. We have the ability to import footprints like cylinder footprint. In my MBXML, there is only one cavity, but there could be multiple ones. I want to assign a library. So my cavity is going to be inside my special cavities, special valves. And I can import. So by doing that, now inside the special valves, if I go to the folder special valves, I will see my cylinder, which has the main drill, and it has all the bolts, 16 bolts, all with a different position, M12. And in this case, there is also an O-ring, so I could see edit O-ring. And if you don't need the O-ring, you can clear and you can remove the O-ring from the cavity. So now if I go to my SolidWorks and I make a new part and make a block, then I start the exercise. But if I want now to test that footprint, I can go into the cavity library. I can go to my special cavities, special valves, take the cylinder, provide a name, cylinder, and that will be the shape. Now the block might be too small. Yes, I need a slightly larger block, otherwise it's not able to fit. So let me make it 230 by 230 and insert again. And now that's my footprint made directly in the block. So by doing that, I was able to take a cavity that I had in another block and import into my library for next usage. This is not the correct way this footprint must be assembled on the block, because I need an O-ring and I need through bolt holes. So we'll test a new functionality that is available in 985 MDTools for SolidWorks, which is already available in the Inventor version as well. So, but I'm not going to do that in this particular block, because like I told you, I want to design a cylindrical manifold, and starting from a square is really not a good idea. I will start from a different shaped manifold and then starting to place cavities there. Before doing that, let me quickly go through some questions. Will depth of feature be referenced from the original block face or assessed face? So in case of, let me get back to the previous sample. The depth is always from the plane where you put the cavity. So if you put the cavity on this face, then the depth in the drill chart or machining callout will be referenced to this face, not to the external of the manifold. And that's how MDTools is designed. So the geometry is defined from the face. So all the depth are referenced to the face, from the face where the cavity is lying to. I see a question from my friend Marco. Hello, MDTools might be seen as an integration of SolidWorks, and cavity library is included in MDTools. Yes, MDTools is a plugin for SolidWorks, and the MDTools library is a part of the software. It is possible to customize it, but we have the ability to create our own cavities, and we have a standard library already included in the software. Let me start. So my purpose is to design a cylindrical manifold. So let me start from scratch. And I want to start with a new part. Now, since I need at the end a cylindrical shape, it's better to start manually. Normally, in these cases, I start with a a polygon, usually an octagon or hexagon, according to how complex the block will be. So let me make an octagon, 8 faces. Let me make it in any position. By default, MDTools, when is loaded into SolidWorks, this is important for those that are not familiar with MDTools for SolidWorks. It's turning off automatic relationships. So in this case, I'll need to put the relationships, but don't turn on a relationship when you are using MDTools. If you need the standard modeling, then simply turn off MDTools. It's not mandatory to keep it loaded, but for a better behavior, it's better to have automatic relationship switched off for MDTools. So my octagon, since eventually I'll need a diameter, let me measure it. I don't remember exactly how much it was. So I go back to the cylinder body, and this one was 118.5 radius. Okay, so let me do here 118.5 by 2. So I'll start from an extrusion, and let's say that I need a 160 millimeter, more or less. MDTools works better with the transparency on. In Inventor, it's done automatically. We work in wireframe and virtually color the block. In SolidWorks, it's a bit different. We apply transparency. For those that are not familiar with this aspect, in order to make this part transparent, you must go to the SolidWorks feature. You can expand and go to the aspect of the extrusion, appearance. And here we go to the advanced illumination, and we can bring transparency up to 100. Usually I like to work with 100% transparency. So basically now we want to have the bolt holes. So I go back to MDTools in the cavity library, and I go to my special cavities, special valves. I take my cylinder. If I look at the diagram, it's called C1. That is the name of this cavity. So let me take the C1. I also provide a network, C1. Since I want a mirror footprint, because I need through bolt hole, the footprint that I have saved into the library is the one with the bolt holes, but I need the true bolt holes. So mirror footprint, insert. I have the possibility to select the type of bolt holes. So I need the M12 through bolt holes. I also want an O-ring, which I have in my library. It's possible to define standard O-ring grooves in the library. Okay, I want to place here, and I put in the origin of the part 0, 0. Okay. So when I do that, MDTools is creating my true bolt holes, the O-ring groove, and everything. So I'm ready to start my design. Since I have made the diagram with Hydro, in order to save a bit of time for today's webinar, I'd like to export the information from the diagram into MDTools. It will not be difficult to design manually without the help of the diagram, but still it's nice to have the diagram made here. So I'll do a couple of commands, networks for the diagram. And with this command, I have created the networks for this circuit. And I'm going to export my diagram into an XML file that I'll use for the block. Export, and that's my manifold. The export has not only the cavities, so as you can see, that's a Sanedolix T19A, it's a large cavity. I have also linked the 3D model. We will see how MDTools is able to do the automatic assembly at the end of the design. Similarly, this is an NG16. It's not super huge, but in this case, I decided to go for a pilot operated direction control valve that's reasonably handling. So in this case, it's 300 liters per minute. And I have a lot of other ports, flanges, BSP ports, and this is a special cylindrical flange. So it's called a cylinder. That's exactly the name that I have assigned to the cavity into my library. So since I have exported the XML file, I can go into MDTools. In this hydroschematic tab, I can load the cylindrical manifold. Now on the left, I have the list of all the cavities that should be present into my design. So as you can see, C1 is already there because I started there. So C1 is already part of my block. All the rest is not grayed out. Since I have a large directional controller, I start from that. So I'll take the item 2 and insert here, and I can place my cavity somewhere here. Just a moment, insert. That's a bit strange. Let me start here, but otherwise I'll need to do a bit differently. Yes, this one works fine. Delete, yes. Let me change face. Let me see if now it's able to place it here. For some reason, it does not like it. Okay, let me change the design. I'll put the valve here. No, I need to change it. I had played with it, but okay, let me do something else. Let me try something different because it looks like it does not like this face. And later I'll do again. Let me yes, looks like there is something else. Let me change the face and try to put it here on the opposite part. Maybe here it works. Okay, looks like I cannot use that particular valve. I go for a cartridge valve and we'll see. Well, I have a manifold I made already, so I'll start from there, removing the other parts, because I want really to do this exercise. Let me get rid of some aspects and then I'll get back to. Let me delete most of the cavities. So these ones, let me delete. Let me clean up a bit. I'm sorry for the inconvenience, but I had practice with the diagram, but looks like for this shape it's not. So I'm here, and later I'll check what was wrong with the other shape. So basically, I am exactly where I wanted to be. Manually, I have the flange, the cylindrical flange, and the NG16 valve here. I can remove the inclination. Later, I'll need to incline some drills from my block. Let me save my block here. And that's my cylindrical manifold. So back to our diagram, hydroschematic. Let me load again the same diagram, cylindrical manifold. I have my NG16 valve already placed, which is item 2. And I have all the other valves that are missing. When designing, I can start from the network, so I can take my purple one, I take my counterbalance valve, and I can place it here. So in case we want to design this cylindrical manifold, we cannot start with the cylindrical shape. We need always to have a flat face. In this case, I can use the MDTools command, connect cavities. In the center, I can do a connect tangent on the opposite side, or again in the center, and click OK. This will create the cavity. I am able to sink the cavity. That's a sunk cavity. So by editing the cavity, I will be able to sink it. Maybe I do a 38 millimeter. In this case, when working on a cylindrical manifold, my intent is to sink a bit the cavity, because later I'll need to remove material from the octagon by making it cylindrical. So I make sure in this case that and this will apply also to the spot face of the ports that I'll be placing shortly. I'll make sure that the shape of the cylindrical manifold will not enter into chamfer where I could damage O-ring when assembling the cavity. Connect cavity command will work if there is a 90 degrees inclination. Otherwise, it's better to use a stretch. Stretch this, allowing inclination up to here. And it is possible to control the 2 degrees of inclination. So we can make simple and compound angles. Beta controls the inclination with respect to the face, while alpha controls just the orientation of the block, of the rotation of the block. And it is possible to change also the length of the drill. In this case, the drill depth will be from this face. Anytime during the design, we can do a connection check. The connection check will verify if we have errors, mistakes in our block. And in this case, there are just unconnected and broken networks. Of course, we have just started the block, the design, so we have a lot of errors, but eventually at the end, we will need to verify all the connections. Now, if we remember the diagram, we had P and T, which we want now maybe one on the top and one on the bottom face. I put the P on top, so I can just expand the network P, insert, and place it somewhere here. I use the 0 as reference, so I can put in the center. If I don't like the position, I can rotate the flange, and I can move it up or down according to the position. It is possible to directly do a connection if you want. Now this will be a bit dangerous because we have other drills, but I'll handle this situation in a different way. And now I cannot really go with this full drill depth, so I need to stretch the drill. I'll make it 50 millimeter deep, and I will add an offset hole. So in this case, it's just a technique. I'll add a 20 millimeter offset hole, and I want to align these two cavities, and I will stretch it to make the connection. 98. So that's one part of the connection. So the pressure is entering into the NG16 valve. One is going to the counterbalance valve. The other port is going to the other part of the cylinder, which is port C2. So I'll take my C2 and put somewhere here. Again, in the center, maybe minus 50. And I'll use the same technique. So I will do offset hole again here. I don't want to incline the entire port. I will just make an incline drills. And I can do stretch this with inclination. And I can save my block. Since for the same statement I made earlier, since I need to remove material, I need to sink a bit this cavity. So edit, and let me make it 8 millimeter deep, so that when I cut the external part to make the cylinder, I will see the full counterbore. I have this is the pilot X. So since I'm here, I will add also the pilot port here and connect it here. And the position can be referenced to another cavity. So dynamically, we can change the position with expert to another cavity and make it 65 by 20. When working from HydroCAD, automatically we have the engraving, as you can see, C2X. I'll just delete them eventually. So it is possible to edit all the engraving, make it non-cosmetic, or delete all. I don't really need all the engraving because later I'll remove all the material, so I'll delete all the engravings. This can be done on one operation directly within the MDTools commands. I need the tank port. So I use the opposite of the P face. So I'll take my tank and insert here. Again, since this is interfering with the bolt holes, I will rotate the flange. I will put at 0. And I can reference with respect to the other cavity, maybe at 0. So in this case, they are aligned on the opposite face. Now I want to make a connection. I need again an offset hole, which will be 18 millimeter, and I can make it minus 5 millimeter. So I'll change. When doing offset hole, it's better you unconstrain to selected cavities, because later the chance you will need to move the the drill is high. So it's better to leave it not constrained to the parent cavity, so then later you have more freedom for modifying it. Stretch, I can stretch and incline. So again, we can do compound angle or simple angle, 0 degrees, it's fine. So let me position it. Let me save, and it's possible to measure the wall thickness. So in order to make sure that we have enough distance. Here we don't have, we have just 1.34 millimeter, which is not enough. So here we have two possibilities. One is possibly moving at maximum here. As you can see, it's touching, really going almost tangent to the original drill, so that will not be a problem. And this we can incline a bit more. Of course, we can do measure wall thickness. Now it's 6 millimeter, it's fine. Or if we have doubt, we don't see really the problem, we have the possibility to run the wall thickness around all cavities. I can see one other issue here, which is this one. So here we have only 3 millimeter between these drills. So in this case, if I had to machine this block, the manufacturer will not be very happy, but now I need to do another inclination. Yes. So for those knowing a bit of manifold manufacturing, this is a cylindrical manifold, so really it's a particular case. But when you are working one phase, unless you have 5-axis machines, you will not really be able to do in one operation incline drill with different direction. So if we take this direction, it's nice, we can do also incline drill very easily on the opposite direction, but if we do vertical, then with a 4-axis machine, this will require a different setting. So it cannot be done in the same operation. Now, what else I'm missing? I'm missing the drain port, which I'll put below with reference to the flange at 0.60. I'll add an offset hole here, just a small one, 6 millimeter, and I'll stretch this with inclination up to the incline drill. 180 degree. I can stretch this drill, maybe 120. And I can move my drill slightly. This I can reduce the depth of this drill, 12, 14 by 25. We can always run the connection check. Start. The connection check will give us all the issues, and there is a broken network, the C2. So I need to connect the pilot for a counterbalance valve. Let me do it quickly. 1/8. I want a tangent connection on the opposite side and moving on the Y direction. In the diagram, there was also a orifice plug here. So I'm going to put a plug here, 1/4. and I'm going to position it somewhere here. I can stretch the drill and make it a bit deeper, let's say 35 millimeter. I want to add an orifice plug, orifice here. I want an M8. And this one, I want to stretch it up to this with inclination. So this will change the entire block, the entire cavity, and then I can find, let me move it on the Y direction. And this one I'll need to sink a bit more. Let's make it 15 millimeter. And this one also I can move a bit. So now my block is good. So I made all the connection. Of course, I could verify, but we are going out of time. So let me start with the rest of the presentation. So I'll need to make this a cylindrical manifold. So I'll need to create a sketch. On the top face, I'll create a circle. And my circle will be tangent to the faces, so I can add a relationship. Well, you could put the diameter or just according to how you are more familiar with geometry. I need to cut the external part, so let me add a larger circle. And I'm going to do a extruded cut. So this technique of starting with a polygon and then making it cylinder is valid also for Inventor. I need to make it deeper. Let me edit. I'll do a through all. The aspect, of course, is taken from the standard aspect of the part. So in this case, I'll do a copy appearance and paste to the extrusion. Well, let me do it from SolidWorks. Copy appearance and paste. Okay, now it's fully transparent. As you can see, MDTools lost the position. Well, it really cut also the bolts, which is not what we want. So in this case, we'll need to add additional operation, something like this. Maybe like this, so we can add dimensions. 1, 1, 2 should be enough. And I can extrude cut. Through all. And similarly, we can make this transparent as well. So let me copy appearance and paste. Okay, so now my block is finished and I can go to the assembly. So I can make a new assembly. I can do an automatic assembly since I have the schematic. I can do the automatic assembly for my cylinder block. This will bring in valves and plugs. So here we can see the valves and plugs. Let me do assemble plugs. They should come. And of course, we can assemble manually. So this is insert component. This is just a SolidWorks assembly, so it will be possible to place other component and mate with all the SolidWorks commands. So we can do mating. And of course, we could add also the bolts. So in terms of assembly, it will be possible to assemble items by using standard MDTools commands. So there is nothing really much different than what normally is happening. Let me show you the machining drawing because really we run out of time, and here I want to spend a bit more, couple of minutes to describe some challenges you might have. So when you do a machining drawing for a non-rectangular block, you might not have faces like in this case. So if we create views with MDTools commands on the non-rectangular block, everything will work. So adding the automatic views will work, but adding the face name might really not be helping at all. The origin is taken from the origin of the part, but in this case, it really might not help at all. So when making views for non-rectangular blocks, I normally don't show the origin and axis. Sometimes I make cross sections according to the needs. So let me create views. I exclude the face name and I exclude also origin and axis. So I create the views without those aspects. Of course, not having an origin does not make sense to automatically dimension the position of the cavities. So for the position, you must go with the manual annotation, like in this case. If you prefer the ordinate dimension, horizontal, then we can create by using SolidWorks commands. So this is nothing new compared to what you normally do without MDTools. What MDTools can help with is with machining callout or drill chart according to which one you need. I show you a limitation here. If we do machining callout at this stage of the block, now the machining callout will show only for those cavities that will have a face. So it will show the machining callout on all the bolts. Those are grouped 16, 13 by 150, all the drills. But in this case, MDTools is not able to create the machining callouts here because there is no face. So a workaround for that is if you go into the part, and that is why it is always better to leave at the end the shape for the cylindrical manifold. If you just move the end of the part slightly up and you leave the faces, then it will be possible to display all the machining callout, even if now you have the octagon, but that's temporary. You run the machining callout. This will work for all the cavities, also for the one that were missing. Let me delete and create. It will work for all the cavities, so also for the inclined ones. And then you can go back to the part and make it cylindrical. So when we go back to the drawing, now you will have both the correct geometry and the information here. It might be worth showing the colors, so internal colors, or creating views showing the internal colors. Whenever you need, you can make a cross section. This is done not with MDTools command, but with standard SolidWorks commands. So as an example, we could make a cross section just to show the intersection here. And the aspect is controlled really by the SolidWorks. Either you want to display according to the view, or so you can do all black and white, or show the internal colors in either cross section or wherever you need. So it is possible to control aspect in all the different aspects of the machining drawing. In case of drill chart, same technique. You must, before doing the drill chart, it's better you switch off the cylindrical shape. You will run the machining ID command. So for those using drill chart, you should be familiar with the machining ID. This command is able to assign to each operation a unique number. There is one important information here. For machining ID, since we have not the standard 6 phases, it's better you use a naming scheme that is not related to the phase. So this one is better, is the first one. So every item will have a unique ID, 1, 2, A, 2B, 3, 4, and so on. And now that you have run the machining ID, in the machining drawing, it will be possible to display the machining ID. Let me get rid of the machining callouts. Normally, if you do the drill chart, you don't. So now you have the number next to each drill. You can make the machining chart. And the drill chart will have all the cavities. The item 13 for 34, and then eventually when you are done, you will need to switch back to the original shape. Back to the question of where is the drill depth starting from, I want to highlight this because this is really an important case. The drill depth is always made from the face where it started. So if you notice here, I added later this planar face in order to be able to assemble the flange. Since the flange was made on the other face, now the depth for this drill in the machining drawing will be different from what is actually in the block. So this is important. It's important to know how MDTools works. So if I look at 20, operation 20, I can see that 8.5 is 24 millimeter deep. But if I make a cross section, that is not 20, 24. It's less. So in this situation, what would be better from a design perspective is always to place not the cavity on a plane where it does not exist anymore, but it's better to use a command that is part of MDTools. So in this case, I like more to use change face and relocate in the new plane. So I can use 0 and the reference to this one. So this will recreate the features starting from that plane. And now entering again in that same error which happened in the beginning. I'm testing the beta version which is not yet released, so I'm sorry for that inconvenience. We'll make sure that in the final release this is not happening. So now, for some reason, it's doing a validation where MDTools is saying it cannot really create the feature. We'll take a look later. I think we ran a bit over time, so I turn it over back to Megan.
All right, thank you, Carlo. That was wonderful, and I think we covered a lot of topics today regarding non-rectangular block design. I believe you've done a pretty good job at addressing all of the questions that have been posted by the audience, and there's a couple in there that I'm about to address right now. But if you have any additional questions, please email us, please contact us, and we will get back with you on those. Yeah, we went over the time today, but that's what we've got. If you didn't get answered and you do email us, we will follow up within 48 hours. Send the email, please, to support@vestusa.com with all of the details of your question. We'd be grateful if you could complete a short survey at the conclusion of today's webinar. Tomorrow, you'll receive an email containing a link to a replay of today's session. So feel free to share this link with your colleagues and rewatch as needed. A link to view video segments from prior webinars will also be provided in the email. As you can see, we have the webinar series posted on various social media channels. We invite you to follow these channels so that you can receive the latest updates from upcoming webinars as well as product releases. Our next webinar takes place on May 29th, where I will provide a refresher on NetScheme, our diagramming software on the cloud, and introduce some of the recent updates and improvements that have been implemented. Also regarding today's webinar, we are planning on releasing the new MDTools Library Manager, the MLM 2025, on June 5th right now. Thank you again, Carlo, and everyone else for attending today's session. Have a pleasant and safe day.